Ok, bueno, acabamos de explorar entonces cómo las simulaciones nos pueden ayudar muchísimo a ahorrar costos, a solucionar problemas técnicos, incluso algo muy interesante que mencionó Laura, a entrenar mediante simulación una inteligencia artificial. Entonces esto es algo supremamente interesante porque se puede aplicar a muchos ambientes, a muchas infraestructuras, ideas, todo se puede aplicar, porque estamos evitando pasar por el proceso engorroso de entrenar, por ejemplo, de las cajas, tomar cajas de diferentes categorías, clasificarlas, seleccionarlas y todo se puede hacer mediante simulación. Entonces, súper genial esa idea. Y ahorita pasamos a una charla que conecta dos mundos muy poderosos, que es la robótica y la medicina. Esta charla viene de otro país, de la India, es de un personaje que trabaja en este momento en Nvidia, y pues puede comunicarse, nos muestra cómo comunicar ROS con 3D Slicer, que es una plataforma de visualización médica en 3D. Entonces, pues, teniendo en cuenta que es de la India, vamos a tener que hacer la exposición en inglés, pero para ustedes no es un problema en eso. Entonces, vamos a pasar ahora a nuestro compañero. ¿Está escuchando?
So, hi, I'm Arvind, and I'm going to be talking about Slicer ROS2. It's a way to integrate 3D Slicer and ROS for medical robotics. This is work that I did as a grad student uh, at Johns Hopkins, and it's being continued to be developed. So, to get started, I'll give a little bit of background on what image-guided robotic interventions are. This is where we integrate sophisticated robotic and imaging technologies to perform minimally invasive surgery. And when it comes to building a robotic image guided therapy system, uh, there are a lot of moving parts. There's generally an imaging device, which is in this case an X-ray machine. There's tracking equipment to keep track of all the different moving parts, like where the human is, where the robots are. There's the actual robot, which in this case is moving the X-ray machine, the imaging device. And there's also the navigation interface. This is what the actual doctor or surgeon sees. And as you can see, there's a lot of things that need to be taken care of. And a lot of companies do provide this, but it comes with really expensive licensing fees. And as developers, we like open source stuff. So when on the image guided side, we have 3D Slicer. It's open source. It's a medical imaging platform. It's really popular in the community. There's 1 million downloads in the past 10 years. And 3D Slicer has its own Python interpreter, and you can have lots of built-in extensions that can be used. So you can do your machine learning stuff, add extensions to use really cool tools like Slicer Monai. You can do calibration, registration. So essentially, a lot of the things that are needed to be done for the medical imaging side of things are already done in 3D Slicer. So when it comes to calibrating a system, 3D Slicer already has tools for that. And as someone who's trying to make something new, you can work on your idea rather than spending time re-implementing things that have already been done. And that's what 3D Slicer helps with. And I know that this image is a little bit overwhelming, but this is everything that Slicer more or less lets you do. And I just want you guys to look at this one small thing here. This is OpenIGT link. It's a networking protocol which lets 3D Slicer talk to a lot of other devices like ultrasound scanners, cameras, endoscopes, yada yada yada. Now, as it's a robotic IGT system, there's also the robotic side. And that's where ROS comes in. This is a ROS conference, so I don't really think I need to explain what ROS does. But when it comes to medical robotics, most medical robots do expose ROS interfaces Or if they don't, they might be using something like the Johns Hopkins SysSaw library for like communication, and that lets you expose ROS interfaces as well. Now, this is a picture of like the Da Vinci robot kit that's being maintained by Johns Hopkins, and that provides ROS interfaces too. Now, when it comes to like using ROS with Slicer, they're like two different islands. Like they don't really talk much to each other, and we needed a way to like get all the niceness from like robotic side and image guidance stuff from the Slicer side to like talk together. And there have been some early attempts to do this. This uses the networking protocol, OpenIGT link, and creates like a ROS IGTL bridge to like make 3D Slicer talk to your robot. But this involves a lot of, again, like it's fairly primitive in its implementation, and you don't get access to all the niceness that ROS, like the full suite of tools that ROS or like 3D Slicer have. And that's where we started building Slicer ROS 2. And some of the folks involved with the ROS IGTL bridge were also involved in this. And what Slicer ROS 2 is a tool that gives access to the full suite of tools in 3D Slicer and ROS at the same time. So this is a Da Vinci patient-side manipulator arm being visualized inside Slicer and being controlled. And the platform can be used to like prototype image-guided robotic systems fairly easily. So this is like a video of like some folks at like Brigham and Women's Hospital, like Harvard Medical School, using Slicer ROS 2 to have a robot alongside MRI images in 3D Slicer. So on the left side, that's the robot being visualized in RViz, and on the right, that's 3D Slicer. So as you can see, like you have like really smooth, like the visualizations are fairly smooth and quite similar to RViz, and it's inside 3D Slicer. Now, why should ROS 2 developers care? Well, Slicer ROS 2 lets you have robot visualizations without needing to write any VTK code, which 3D Slicer needs. And similar to RViz, you can have the robot, but co-located with like the medical images. And we also make it possible to like integrate a lot of the ROS client library features directly in Slicer. So you can have like your publishers and subscribers and the TFs, parameters, service clients, all of that. And you don't need to spend a lot of time wiring things up. It works fairly straight out of the box. Yeah, so how does it work? Like, why does this work, and why is it better than like the ROS IGTL bridge? Well, to start with, on the ROS side of things, we treat 3D Slicer like it's a ROS node. So it's like, it's a ROS node. Like as far as ROS is concerned, it's behaving like a ROS node. And on the Slicer side of things, all the ROS communication mechanisms are essentially packaged as murmel nodes. And I'll spend a bit more time on what murmel is in the next slide. But what this means is you essentially have a Slicer murmel node for like publishers and another murmel node for like a particular subscriber. And you get to like set it up like that, which allows for like really rich communication between ROS and 3D Slicer. Now, in this slide, I'm just going to go a little bit over what murmel is. And murmel stands for like medical reality modeling language or something like that. And it's a logical unit inside Slicer. And all the data is organized using murmel nodes. It's a little confusing that like, Slicer, like murmel is also nodes, and we have nodes on the ROS side. But yeah, that's the confusion we have to deal with. But all the data is organized inside murmel nodes. So as you can see in the image, so publishers have like corresponding normal ROS to publisher nodes. And this is like a really rich thing. So you can add observers to like these murmur nodes so that when changes happen, you can, so like let's say a change happens inside a murmur node, you can essentially use that event to maybe publish a message and like have that be picked up on the ROS side. You can also like have other things like save and restore state, search for nodes by name and type, and murmur nodes also have this like type of murmur nodes called murmur transform nodes, which more or less represents transformations, which is perfect for representing robot transform chains from the ROS side in 3D slicer. And that's not stuff that you could have done previously with the ROS IGTL bits, or it would have been possible, but would have taken a lot of writing. This is like a video that my colleague is like moving a cobot, and you see that on the left side, that's like RViz, and on the right, that's like 3D slicer. Very responsive. And here you can see two robots side by side. That's a small Omni robot, and that's a Da Vinci patient side manipulator. And it's like, and it's really easy to do in like Slicer ROS 2. Going into core capabilities, you can add publishers and subscribers for any custom message. There's TF2 integration, you can like broadcast or look up transforms pretty easily. Parameter clients for like querying any parameters that's like active. And you can also use like ROS2 services as a client. It has like a 50 hertz default spin rate that can be changed based on your requirements. And it supports robot visualization. You can just directly load your URDF files, and it sets it up pretty easily. And it has support for all ROS2 message types with the ability to write your custom message types. This is just another slide going over like the types that are matched and like how it's converted between ROS and slicer. So on the slicer side, we have like the standard strings, and that's converted into the corresponding ROS message strings. And this is done by default. And these are just like common ones that we have wrapped easily. There's a custom one you want to add that can also be done. And what can this be used for? So this is like Slicer ROS 2 in action. It was done in collaboration with Dr. Axel Krieger at Johns Hopkins, and that's a Da Vinci robot. And as you can see, inside Slicer, for a tongue tumor removal task, we are drawing the path inside Slicer, and we can use that to control a robot externally. And I know the video is a little underwhelming, but this used to be incredibly hard to do. And how do you use this? So the slicer has its own like Python console, and you can write pretty straightforward code like this. So you create and add a publisher. In this case, it's a string publisher, and the topic that you want to call it is my string, and publisher.publish, and that's it. If you want to have something a little more difficult, if you want to send like a matrix, a pose. In this case, it would be BTK Mammal ROS to publisher pose node. I know the name is really long, but there's also a shorthand for it, wherein you want to send a pose, and the topic you want to create is like my matrix. You essentially publish a matrix, and that can be picked up on the ROS side. The API is really simple, and it's pretty much very similar for like all the other RCL stuff too. Now, when it comes to the robot visualization workflow, just like RViz, you can essentially just add your robot directly. So you launch a robot, launch the robot state publisher, and in the Slicer ROS 2 extension UI, you just put in the name that you want and like the parameter node for like the robot state publisher, and load the robot. That's it. And it'll be added in. It's really straightforward. And I just want to like, show this being used for like a fairly straightforward use case. And I'm going to use breast cancer tumor removal as an example. Now, when it comes to like a surgeon removing a breast cancer tumor, he or she has to make sure that when he's cutting it out, none of the tumor is left. So we need to have a warning when the surgeon's cutting a little too close. And to do something like this, we can set it up such that there's haptic feedback on the robot that the surgeon is holding when he's getting a little too close. And this is the same thing in action. So we're going to use that white bold thing to kind of assume that that's the region where the surgeon shouldn't get a little too close. And when the knife or the cutting tool is getting a little too close, you see that it will turn red. That means it's in the forbidden region and the surgeon is receiving haptic feedback that it's bad. And to implement something like this, it's only like 13 lines of code. So you set up like your publishers, you add your observer, and then you add the logic for when it's a little too close. And this is like the shortest implementation of a virtual fixture that we've had. And yeah, that's what Slicer ROS 2 lets you do. Of course, this was not really a one-person effort by any means. There's like a lot. We're like really grateful for all the people who funded this, and the brains behind this was mainly Anton. He maintains the Da Vinci Research Kit at Johns Hopkins. He's a research engineer there. All of his work is like really cool. You guys would love checking out his like GitHub repositories and everything. And Laura was like the PhD student who was like primarily involved with all of this stuff. And we had like a ton of advisors, including some really big names like Dr. Junichi, like Dr. Axel Krieger, Dr. Peter, Russell, and Simon. And this has been used by the community to like do some pretty cool things. This is some folks at Norway, and in the interest of time, I'm not really gonna like go into the details of this. And this is like some folks at like Georgia Tech, and they're doing like pretty advanced stuff with this. Of course, we have spent quite a lot of time maintaining the documentation for this, and we are actively taking in requests. So if there is something that's missing, feel free to reach out, open PRs, and like contribute. Like we would love it if like people started using this more. And yeah, that brings me to the end of what I wanted to share. I hope you guys enjoyed it.
Well,
yeah, and you can scan the QR.
okay. A big thank to Aravind for connecting with us all the way from India and showing us how he can integrate ROS2 with Slicer. It's always so inspiring hearing someone with that much experience in the field. And we hope to see you in other occasion like this. Thank you so much, Aravind.
Oh, thank you. And feel free to reach out to me if there's like anything I can help with on the Slicer side. I can also put you guys in touch with Anton. Yeah, that's my contact info there. Thank you.
Thank you so much.